Hi, I'm Jeongeun Park. I'm a student of Ewha Women's University in Korea. What I'm going to talk about is somewhat homomorphic encryption-based, compact and scalable private information retrieval. This is a joint work with Mehdi Tibouchi of NTT Corporation in Japan. I first introduce what private information retrieval is, then I'll give you previous efficient protocols, and I introduce our protocol SHECS-PIR, then compare it to previous results. Finally, I will give you our experimental result. What is private information retrieval? It is a protocol between a client and a server. A client requests an item of large database which is owned by a server. Then the server gives the correct answer without knowing which item the client wants to retrieve. There are two basic types of PIR, one of which is information theoretic PIR. It has the advantage that server's computation cost is relatively inexpensive due to bit operation for each entry, and it guarantees information theoretic privacy. However, it was proved that transferring the entire database to the user has optimal communication complexity with a single server. It means that non-colluded multiple servers are required for low communication complexity. The other one is computational PIR. It can be used with a single server under cryptographic hardness assumption, and it has lower communication cost than ITPIR. However, it takes much more computational cost due to cryptographic operation. We focus on CPIR based on homomorphic encryption schemes in this paper. Homomorphic encryption allows a computation over ciphertext. It can be applied to a privacy-preserving outsourced computation. For example, a client who does not have enough computation power can request a computation over its own data to a server. For privacy, the client encrypts its data and gives them with a function f to the server. The server computes over the ciphertext with the function f, then gives the result to the client. Then the client decrypts the result with her own secret key to obtain the desired function value. There are efficient CPIR protocols, XPIR and SEAL-PIR. XPIR is the first computationally efficient CPIR based on BGP homomorphic encryption. It has simple structure. Let the number of database 25, and the client wants to retrieve the third item, for example. Then the client generates a query vector of dimension 25, where only the third component is encryption of 1, and others are encryptions of 0. The database of the server is also a vector of dimension 25, and server performs dot product between the query and data vector, and the result is an encryption of desired item. However, this approach makes large network cost. Query contains n number of ciphertexts. If n is 1 million, it takes huge network cost. Therefore, they use Stern's method to improve network cost by structuring database as a d-dimensional hypercube. Let the number of database is 25 and the dimension be 2. And the database is not a vector anymore. It is a 5x5 matrix. A client wants to retrieve an item located at 3.2 here. Then client needs a query for row and column. For row query, only the third component is encryption of 1, and the second component is encryption of 1 in column query vector. After multiplication between query and database in this order, the result is encryption of desired item. As a result, the number of ciphertexts per query is reduced to 10 comparing to 25 with the previous way. This is how SHECS-PIR works. Then, SHECS-PIR optimizes the query size of SHECS-PIR by giving extra work to a server. A client represents the index as a monomial for each dimension. Then server obliviously expands a query ciphertext to a query vector for each dimension. Let's consider the same example of SHECS-PIR. The desired item is located at 3.2. For the third row, a client encrypts x to the 2, then the server expands the ciphertext to the row query vector, where only the third component is encryption of 1. For the second column, the client encrypts x, then the server expands it to a column vector, where only the second component is encryption of 1. And the procedure is not expensive. However, what if the number of databases is larger than the plain text polynomial degree? Then clients needs more query ciphertext or make the polynomial degree larger. Both protocols try to avoid expensive operation, which is multiplication over ciphertext. And both protocols use a multiplication between plain text and ciphertext, which is less expensive. So it results in larger response of server with the crypto system's expansion factor F, which is a ratio between ciphertext and plain text. The reply procedure is the following. First, a server computes a multiplication between row query vector, which is a ciphertext, and database matrix, which is a plain text. Then the result is a ciphertext vector. In fact, the ciphertext space is much larger than plain text space in lattice-based crypto system. Therefore, the server should divide the resulting ciphertext vector elements into F chunks to fit in the plain text space for using less expensive operation. Finally, repeat the first step with a column query vector, which is a ciphertext. As a result, a client receives answers with f to the d-1 ciphertext. This is how SHECS-PIR and SHECS-PIR work. Now, I introduce our protocol based on totally different approach. In query generation, a client chooses an index and binarizes it. We have log n epsilon j, then she encrypts each epsilon j, then send these log n ciphertexts as a query. In server's computation, server structures database element as a lookup table below, like the table 1. According to epsilons, database elements xi's are stored as this lookup table. And the data elements are chosen by a mux gate by depending on epsilon, like the binary decision tree, like the figure 1. So if epsilon 0 is 0, x0 is chosen after this mux gate, and x2 is chosen after this mux gate, and this epsilon 1 is 1. Then x2 is chosen after this gate. This is how mux gate works. In our protocol, these epsilons are encrypted by a client. Nevertheless, the mux gate gives correct answer without any problem due to homomorphic encryption. Then the desired data, xi, is obliviously chosen as a ciphertext. Then server gives the result to the client. Of course, we can optimize query by packing query technique A client binarizes the index I and packs each epsilon to each coefficient of a polynomial, like this. Then she encrypts this polynomial. In other words, instead of encrypting each epsilon, the client encrypts a polynomial as a query. Then a server needs an additional step called query unpacking to unpack the query as encryptions of the epsilons, that is, log and ciphertext. This is query unpacking procedure. The server obliviously unpacks each coefficient as a ciphertext, and this step takes somewhat large time due to large constant in our implementation, even though its complexity is O log n. We instantiated our protocol based on TFHE homomorphic encryption scheme. TFHE is GSW-style homomorphic encryption scheme, which enjoys a slow noise growth. Lattice-based homomorphic encryption ciphertext contains a noise term, and it gets larger after homomorphic operation. If the noise is too large, decryption failure may happen. Therefore, the slower the noise grows, the deeper circuit we can build with the scheme. So TFHE is very proper for evaluating the deeper circuit with its homomorphic MUX gate without expensive procedure bootstrapping to reduce the noise or avoiding decryption failure. This table shows that our protocol has less communication complexity. We have two kinds of implementations, with query optimization and without it. So query has log n complexity, which is much smaller than others. And if we apply query optimization, it becomes smaller. And we do not have a factor f in answer in both cases. The first step is an additional work of a server, query unpacking in hours and query expansion in SHECS-PIR. We do have less complexity either, but main computation has additional factor L, which is TFHE parameter. We set it to in our implementation. Therefore, there is very small overhead in main computation. Thanks to additive noise growth of TFHE scheme, the noise grows with log n complexity in hours, like I said before, whereas SHECS-PIR has log n. We observe how fast the noise grows in terms of noise budget. In other words, we observe how much noise has left until decryption will fail in our experiment. So in this table, NB denotes noise budget and Q-U denotes query unpacking. We still have 8 bits until decryption will fail, whereas SEAL has 7 bits left with the same number of data. And NB decreases slower than SEAL, and we can see that query unpacking barely affects the noise budget because there is no difference between the two cases. Thanks to slower noise growth, we can support a very large database before this budget is reduced significantly. We have same query size, but 10 times smaller answer size. For the computation time of the database in this applicable range, the main computation time scales very close to linear with n, and it is similar to SHECS-PIR. We have small overhead over SHECS-PIR due to the choice of avoiding any database preprocessing. This preprocessing is servers preprocessing to set each database element as a FFT or entity form in advance. For saving FFT or entity conversion time, which is not negligible, SHECS-PIR stores the database as an FFT or entity form. Our data is stored as a plain text of which size is 5 times smaller than FFT or entity form. As a result, we have almost no storage overhead for the database in memory compared to an overhead of SHECS-PIR. So this lets us support very large database up to 2327. Whereas the same could not be achieved with SHECS-PIR on commodity hardware. For large databases, we necessarily increase the dimension of database D of SHECS-PIR because it simply fails if D is set to 2 for n is larger than 2322. Even with set D to 3, we could run it only up to n is 2324, with larger instances too big to fit in memory, our relatively high-end server. The communication cost consists of both query and answer size is expressed in the number of ciphertexts. Comp query denotes compressed query, which is query optimization in each protocol. We can see that our total communication cost, even without query optimization, is actually lower than SHECS-PIR with query optimization for large databases due to the much larger answer size of SHECS-PIR. Moreover, query unpacking becomes relatively negligible for large database sizes. It would be natural to use this optimization and enjoy our close to optimal communication complexity. And we have still 6 bits until decryption fails, so we can support more databases. This is my presentation. Thank you for your attention.